Hello, children. So continuing with the preparation of alkyl halides, if you remember last time I told you, alkyl halides can be prepared from alcohols, for which there are three methods. Can be prepared from aliphatic hydrocarbons, that is alkanes, alkenes, and alkynes. In this category also there will be three methods, and there are some special methods for the preparation of alkyl halides. Under that category, we'll study four methods. So in the previous video, I told you we started with the preparation of alkyl halides from alcohols, and out of three methods in this category, we finished one method, that was reaction of alcohols with hydrogen halides. That was a pretty lengthy method. Now coming to second method of preparation. Second method is by the reaction of alcohols with phosphorus halides. Alcohols with phosphorus halides. You know, phosphorus has variable valency of +3 and +5. It means phosphorus forms pentahalides and trihalides. We'll consider reaction of alcohols with phosphorus pentahalides and phosphorus trihalides separately. Alcohols react with PCl5 and lead to the formation of chloroalkane, RCl plus POCl3. POCl3 is called phosphoroxychloride. This is also called phosphoryl chloride, PHOS, PHORYL, phosphoryl chloride, and is also called phosphorus oxychloride. So this is the preparation of chloroalkane from alcohol by reaction with PCl5. But if we try to prepare bromo and iodo by this method, then we'll have to use phosphorus pentabromide or phosphorus pentaiodide. But phosphorus pentabromide and phosphorus pentaiodide are not only unstable, they are highly unstable compounds, and therefore they cannot be prepared even in situ. If you remember, I told you about in situ preparation of an unstable compound last time. So they can't be prepared even in situ because they are highly unstable. Now, coming to the preparation by using phosphorus trihalides. If we use PCl3, alcohol reacts with PCl3 and leads to formation of chloroalkane, and H3PO3 is phosphorus acid. There shouldn't be any confusion. H3PO3 is phosphorus acid. H3PO4 is phosphoric acid. Similarly, H2PO3, that is hypophosphorus acid. So leads to formation of chloroalkane. But again, if I want to prepare bromo and iodo product, I'll have to use PBr3 or PI3. PBr3 and PI3 are unstable compounds, and they are prepared in situ. They are not highly unstable, they are unstable, and they are prepared in situ by the reaction between halogen and red phosphorus. What does it mean? It means if I want to prepare bromo or iodoalkane by using alcohol and phosphorus trihalide, I'll have to take halogen. Halogen means it may be bromine or iodine, plus I'll take red phosphorus in the reaction flask, plus I'll take alcohol. This halogen and phosphorus will react and lead to the formation of phosphorus tribromide or triiodide. As soon as this trihalide is formed, it will attack alcohol and lead to the formation of final product. So reaction involved will be 2 phosphorus red plus halogen. Halogen may be bromine or iodine, gives 2px3. Now alcohol and px3 react together to give 3 alkyl halide plus H3PO3. Right? This was the second method. Third method from alcohols is by the reaction of alcohols with thionyl chloride. Thionyl chloride. Thionyl chloride is SOCl2. So alcohol is reacted with SOCl2 This reaction is carried out in the presence of pyridine. What is pyridine? Why do we use pyridine? I'll tell you. And this leads to formation of chloroalkane plus SO2, which is a gas and therefore escapes, HCl gas, which also escapes. This method, first of all, this method is called Darzon's method. D-A-R-Z-E-N. Darzon's method. Now, some points about this reaction. First point, this method is only for the preparation of chloroalkanes, not for bromo and iodoalkanes, because SOBr2 and SOI2 are highly unstable compounds. Second point, this is a good method, very good method for the preparation of chloroalkanes because these byproducts are gaseous and therefore they escape from the reaction flask so that purification of the product is easy. Third point, what is pyridine? Why do we use it? This compound is pyridine. It's a heterocyclic compound. Nitrogen carries one lone pair of electrons. And this compound is a lone pair donor. And you know, lone pair donors are Lewis bases. So this compound pyridine is a base. Why do we use it? Because this basic compound will neutralize some molecules of HCl which will be left trapped in the reaction flask. See, although HCl is a gas, it will escape from the reaction flask. But still, some molecules of HCl will be left in the reaction flask to neutralize these acidic molecules of HCl. Basic pyridine is used so that they neutralize each other, and again purification of the product becomes easy. So we studied three methods to convert alcohol into alkyl halide. In some simple words, what happens in these methods, in these reactions, is OH is replaced by OH group is replaced by halogen. Now the question comes, can we use same three methods to convert phenol into aryl halide? Because if you want to convert phenol into aryl halide, we'll have the feeling that it's again the same type of method, same type of process. We have to replace OH by halogen. So can those three methods be used for the conversion of phenol into aryl halide? The answer is no. But why not? We cannot use those three methods to convert phenols into aryl halides, which can be understood only on the basis of resonating structures of phenol, which I'm drawing on the board now. See, in the concept of resonance, which we might have studied in 11th standard, we say that the actual structure is not represented by any one of these resonating structures. Actual structure is intermediate between these structures, which we have to just imagine. We cannot draw on paper, we cannot draw on board. Now, if we consider an alcohol, bond between carbon and oxygen is a single bond. But in case of phenols, according to first and the last structure, this is a single bond. But according to remaining three structures, this is a double bond. It means actual bond between carbon and oxygen in phenols is neither a single bond nor a double bond, but it is certainly in between single and a double bond. Means slightly more than single bond, slightly less than a double bond. This is called a partial double bond. And definitely a partial double bond will be stronger than a single bond in alcohol. This is the reason this partial double bond in phenols cannot be broken by those three reagents which were used to convert alcohols into phenols. And this is the reason those three methods cannot be used to convert phenols into aryl halides. So these were three methods to convert alcohols into alkyl halides. Now coming to second category of preparation. Second category is by the by halogenation of, rather I should say, preparation from aliphatic hydrocarbons. Now under this category also there will be three methods. First method is by direct halogenation of alkanes, means by the direct reaction between alkane and halogen. Now in this case, alkane is reacted with chlorine or bromine. Why not other halogens? That I'll tell you later. Alkane is reacted with chlorine or bromine in the presence of sunlight or at high temperature, which leads to successive replacement, one by one replacement of hydrogen atoms by halogen atoms. For example, if I consider methane and halogen is chlorine or bromine, in the presence of sunlight, for any radiation, I can write h nu. H is Planck's constant, nu is frequency. Or we use a high temperature of 773 Kelvin. One hydrogen is replaced by halogen. This can further react with halogen under similar conditions. One more hydrogen will be replaced by halogen, and this process goes on and on. That's why I said successive replacement of hydrogen by halogen atoms. It means this method will lead to the formation of mixture of products, monohalides, dihalides, trihalides. We get a mixture of products. That is why from laboratory point of view, it's not a good method. Yes, from industrial point of view, this is a good method. It's quite a cheap method. This is a free radical process, right? This is a free radical process. Details we are not taking up here. It's not required in 12th standard. This is a free radical process. Now, if there are more than 2 carbon atoms, if there are, let us say, 3 carbon atoms, means propane will have 1 secondary carbon and 2 primary carbon atoms. So in this reaction, reactivity of hydrogen atoms decreases in the order tertiary, more than secondary, more than primary. I'll repeat, in this reaction, in this method, reactivity of hydrogen decreases in the order tertiary, more than secondary, more than primary. Means what? I'll give you an example. Let us say I react propane with chlorine. These are primary and primary carbon atoms, means there are 6 primary hydrogen atoms and this is secondary carbon. It means there are two secondary hydrogen atoms. Since the reactivity of secondary hydrogen is more than the reactivity of primary hydrogen, reaction will take place as second carbon, not at first carbon atom. So the product obtained will be this is the product formed. So it's not that you attach halogen randomly anywhere you want. No, it depends on the reactivity order of hydrogen atoms in alkanes. As I said, in this method, we use only chlorine or bromine, but why not other halogens? See, if we use fluorine, then due to very high reactivity of fluorine, reaction will be highly vigorous. It will be uncontrollable reaction. Therefore, fluoro compounds are not prepared by this method. Second, if I try to prepare iodo compounds by this method, in that case, there are two problems. First problem is reaction with iodine will be very slow. It's too slow to carry out. Second problem is if I use iodine, no doubt iodo product will be formed, although reaction will be slow. There are two problems. One I said is slow reaction. Second problem is this HI formed is a reducing agent. This will reduce iodoalkane formed and will lead to the reverse reaction. But both the problems can be tackled. For slow reaction, we can use a catalyst. And for HI, we'll have to remove HI so that backward reaction does not take place. For HI, we use an oxidizing agent in the reaction flask. So in this case, if I react alkane with iodine, to speed up the reaction, I'll use a catalyst, and the catalyst uses ferric iodide or aluminium iodide. Second problem, HI. To consume HI formed during the reaction, in the reaction flask itself, we add concentrated nitric acid. Nitric acid is an oxidizing agent. So in this flask, we also add concentrated nitric acid. Now, what is the role of nitric acid? Nitric acid will react with HI and convert HI into iodine. So 2HI plus 2HNO3 gives iodine plus 2NO2 plus water. 2 iodine, 2NO2 plus water. Iodine, 2NO2 plus 2 water. I add them. This will give 2 alkane plus 2 iodine and 1 iodine on the right hand side. Overall, 1 iodine on the left plus 2 HNO3 in the presence of catalyst. Let us say FeCl3, FeI3 gives 2 molecules of iodoalkane, 2 NO2 and 2 water. Now, if you look at the overall reaction, this added up. Number one, slow reaction has been made fast by using the catalyst, that is FeI3 or AlI3. Second problem was HI. You can see there's no HI in the final equation. No HI means a backward reaction will not take place, and we get the final product iodoalkane. Second method is by the addition of HX, hydrogen halide, to an alkene or alkyne. In this method, if you remember, you might have studied about addition according to Markovnikov or anti-Markovnikov rule. All that we are going to study here. If alkene is symmetrical, then this then then HX will be added to a symmetrical alkene, and we get only one product. I'll give you two examples. Ethene plus HX. First of all, convert double bond into single bond. Think of two parts of HX. Addition will be HX or XH. Both are same products, they are not different. So when alkene is symmetrical, addition of HX will give only one product. Another example. First, convert double bond into single bond. Add HX, XH. They are also same. It means if the alkene is symmetrical, we get only one product. We do not get two different products. However, if alkene is unsymmetrical, we get two different products. One product formed is, if you use propene, one product formed is 1-halopropane. The other product formed is different, that is 2-halopropane. Remember, both the products are formed, but one of these two is the major product that is obtained in more quantity, and the other is minor product which is formed in negligible amount. We'll always be concerned with the major product, nor the minor product. How do we decide major product formed during the reaction? That is decided on the basis of Markovnikov's rule. There are two simple statements for Markovnikov's rule. First statement, although is not a scientific definition, but if this works, if this can be applied, you'll be able to save time. First definition is more gets more. That's it. More gets more. Means what? If you want to apply this statement, more gets more, you have to look at those two carbon atoms which have a multiple bond between them. Out of these two carbon atoms, that carbon which is already linked to more number of hydrogen atoms, means this one, will get more hydrogen from HX. Means H will go to this, definitely halogen will go to the other carbon. It means if I apply more gets more, then major product form will be second product, minor product will be the first product, and in the exam will write only the major product, not the minor product. But this statement is not applicable in all cases. I'll give an example. Let us say alkene is 2-pentene. In this case, alkene is unsymmetrical. Both the carbon atoms which have a multiple bond between them, they are linked to same number of hydrogen atoms. It means we cannot apply the statement more gets more. Let me write products. One product is 2-halopentane, the other is 3-halopentane. But we cannot decide major and minor product on the basis of more gets more. Now we'll have to study the proper definition of Markovnikov's rule. So proper definition says that during addition of an unsymmetrical reagent, unsymmetrical means the reagent which is being added has two different parts. Both the parts are not same. If it is X2 halogen, X2 molecule has two parts, X and X, both the parts are same. It means it is symmetrical. HX is unsymmetrical because its two parts are not same, they are different. So Markovnikov's rule states that during addition of an unsymmetrical reagent to an unsymmetrical alkene or alkyne, negative part of the addendum means something which is being added. This is addendum. Negative part means X minus. Negative part of the addendum goes to that carbon atom of multiple bond which is linked to a longer alkyl chain. You can see this is linked to a longer chain of two carbon atoms. This is linked to a shorter chain of one carbon atom. So I'll repeat, negative part of addendum goes to that carbon atom of multiple bond which is linked to a longer alkyl chain. This definition is incomplete. I'll complete. Let me decide the product on the basis of what I said so far. Negative part will go to this carbon. This is the major product. We apply the same statement, same parts of the statement. Negative part means this goes to this carbon atom because this is linked to a longer chain of one carbon atom. This is linked to a chain of 0 carbon because there's no chain attached to it. So 2 halo will be the major product. Now I'll read out the complete definition of Markovnikov's rule. It says that negative part of addendum goes to that carbon atom of multiple bond which is linked to a longer alkyl chain or which is more alkylated. More alkylated means which is attached to more number of alkyl chains. This is attached to one alkyl chain. This is attached to 0 alkyl chain. No alkyl chain, right? Or third part says negative part goes to that carbon atom which is linked to lesser number of hydrogen atoms. This is attached to lesser number of hydrogen atoms. This is attached to more number of hydrogen atoms. So this is the complete definition of Markovnikov's rule. We apply the same statement for the addition of HX to an alkyne. Let us see. Triple bond has 2 pi bonds. Break one pi bond at a time and add one molecule of HX. I can use a simple definition, more gets more. This is attached to more number of hydrogen atoms. This is attached to lesser, that is 0 hydrogen. H will go to this, it becomes 2, X will go to this. Product has 1 pi bond left. It means one more molecule of HX can be added. Now for writing the product, I'll first break double bond and convert into single bond. Now I'll add 2 parts of HX applying Markovnikov's rule. Again, I can use more gets more. This will link to more number of hydrogen atoms. So hydrogen of HX will go to this. It becomes CH3. Halogen goes to this carbon atom. So product formed is 2,2-dihalopropane. Right? Now, if we consider addition of HBr, now what I'm going to explain now, that is only for the addition of HBr. If HBr is added and that too in the presence of an organic peroxide. Organic peroxide may be benzoyl peroxide, even sometimes inorganic peroxide like hydrogen peroxide is also used. So addition of HBr in the presence of an organic peroxide takes place according to anti-Markovnikov's rule, means opposite of Markovnikov's rule. This anti-addition is called Harash effect, K-H-A-R-A-S-C-H. This is called Harash effect, or this is also called peroxide effect. I'll give the example. For example, if we consider propene OP means organic peroxide, right? If we add HCl in the presence of organic peroxide, addition will take place according to Markovnikov rule. Because anti-Markovnikov is applicable only for HBr, not for HI or HCl. That is, more gets more. If we add HBr, but if HBr is added in the absence of peroxide, in that case also Markovnikov's rule will be applicable. Markovnikov. Remember, if HBr and organic peroxide both are used together, then only we'll have to apply anti-Markovnikov rule. Markovnikov says more gets more, anti will say less gets more. Less gets more means this carbon which is linked to lesser number of hydrogen atoms will get hydrogen from HX, from HBr. So the product this time will be CH3, CH, CH2, Br. So this product is written on the basis of anti-Markovnikov's rule. Now, third method for the preparation of alkyl halides from aliphatic hydrocarbons is by the addition of halogen to alkenes and alkynes. Alkene has one pi bond. Alkyne, that is triple bond, has two pi bonds. Alkenes and alkynes will react with chlorine or bromine. Why not fluorine and iodine? The reason is same. Reactivity of fluorine is very high. Reactivity of iodine is very low. So only chlorine or bromine are used. These two halogens, chlorine or bromine, can be dissolved in water and used, or they can be dissolved in carbon tetrachloride as solvent and used. Two parts of chlorine or bromine will be same, that is ClCl or BrBr. Water or CCl4 as solvent. This halogen used is chlorine or bromine. In place of one pi bond, two parts of X2, that is X and X, will be added and we get a vicinal dihalide. In case it is an alkyne, in place of one pi bond, again two halogen atoms will be added on adjacent carbon atoms. Similarly, in place of second pi bond, two more halogen atoms will be added and we get a tetrahalide. So alkenes will lead to formation of dihalide, vicinal dihalide, and alkynes will lead to the formation of tetrahalide. You know, bromine is brown in color. Naturally, it's a solution prepared in water or prepared in CCl4 that will also be brown. And during the reaction, if it is bromine, then bromine will be consumed. And if bromine is consumed, then there will be decolorization of bromine water during the reaction. And if there is a color change during the reaction, reaction can be used as a distinguishing test, or we can say bromine water can be used for the confirmation of presence of unsaturation in the given hydrocarbon, right? So if the given hydrocarbon is reacted with bromine water and bromine water gets decolorized, it means given hydrocarbon is unsaturated. It contains a double bond or a triple bond. Now, there's a special reaction in this category. Alkenes, not alkynes, alkenes react with chlorine or bromine in the presence of UV light, ultraviolet light, and do not give this type of addition product. Rather, they lead to the formation of an allylic halide by a substitution reaction. Let me give an example, then I'll explain. Propene with chlorine or bromine in the presence of UV light. These three hydrogen atoms of CH3, these are allylic hydrogen atoms. Reactivity of allylic hydrogen is high. Therefore, when the reaction is carried out in the presence of UV light, addition reaction does not take place at pi bond. Rather, replacement of one allylic hydrogen by halogen takes place, and we get allylic halide, right? If we consider cyclohexene, same conditions, then these are two allylic carbon atoms. Reaction will take place at one of the two allylic carbon atoms, and the product will be, this will be the allylic product formed. For allylic halogenation, we can also use NBS. NBS is N-bromosuccinimide. N-bromosuccinimide. So in place of halogen in the presence of sunlight, we can also use NBS. That will also lead to allylic halogenation in this reaction. For example, these are two allylic carbon atoms, and the reactivity of secondary is more than primary. Both are allylic, but the reactivity of secondary is more than primary. Reacted with NBS. What is NBS? I'll like you tell you. This is N-bromosuccinimide. This will lead to formation of allylic halide. Rest you need not write. This halogen bromine will be replaced by hydrogen atom, that is succinimide. So product obtained will be secondary allylic halide in this case. Now coming to third category of methods of preparation of alkyl halides is preparation by some special methods, some other methods. As I said earlier, we'll be studying 4 methods under this category. These are very small methods. First method is to prepare an iodoalkane from other alkyl halides. If I want to convert chloro or bromoalkane into iodoalkane, reaction is carried out with aqueous solution of sodium iodide or potassium iodide. This reaction is carried out in the presence of acetone as solvent. This reaction to prepare iodoalkane from chloro or bromoalkanes is called Finkelstein's reaction. Finkelstein's reaction. Now, what is the role of acetone? First role I said is it acts as a solvent for Rx during the reaction. Second rule, acetone is an organic compound. This product formed KX. KX is ionic compound. And ionic compounds are soluble in polar solvents like water, insoluble in organic solvents. So KX form will be insoluble in acetone. Since it does not dissolve, it means KX will not ionize to give K plus and X minus ions. Since X minus ions are not produced due to acetone, backward reaction will not take place. So second rule of acetone is KX formed is insoluble in acetone, therefore does not ionize to liberate halide ions, so that backward reaction is prevented. So this is Finkelstein's reaction. Second method is preparation of bromoalkanes from silver or sodium carboxylates. Silver carboxylate means silver salt of carboxylic acid. Sodium carboxylate means sodium salt of carboxylic acid. RCOAG is silver carboxylate. Similarly, RCONA is sodium carboxylate. It is reacted with bromine. In the presence of diCCl4, carbon tetrachloride in this case is acting as solvent, no other role. This leads to formation of a bromoalkane plus carbon dioxide and AgBr. Now look carefully. This alkyl halide, bromoalkane formed, contains one carbon atom less than the starting salt of carboxylic acid. This carbon is eliminated in the form of CO2. If organic product, this is not organic product. If one molecule of organic product contains less number of carbon atoms than one molecule of organic reactant, then the reaction is called a step down reaction. Step down. Similarly, if number of carbon atoms is more, then we call it a step up reaction. So I can say this is a step down reaction, and the name of this reaction is Hunsdiecker-Borodine reaction. This is called Hunsdiecker-Borodine reaction. Third method. Third is preparation of fluoroalkanes. This is the only method of preparation of fluoro compounds in halides. Preparation of fluoroalkanes from other alkyl halides. In this method, chloro or bromoalkane is heated with some metal halides. I'm taking the example of silver halide, silver fluoride, and this will lead to the formation of fluoro product. First of all, this reaction is called Schwarz reaction. Schwarz reaction. In place of AgF, in place of silver fluoride, we can also use Hg2F2, or we can use COF2, cobalt fluoride can also be used, or we can use antimony trifluoride. Any one of these metal fluorides can be used when heated with silver, when heated with bromo or chloroalkane will lead to the formation of fluoroalkane. All the methods will be called Schwarz reaction. Last method in this category is preparation of geminal dihalides. Geminal, I told you earlier, two halogen atoms attached to the same carbon atom. preparation of geminal dihalides by the reaction of aldehydes and ketones with PCl5. So when if one of the R's is hydrogen, it is aldehyde, otherwise it is a ketone. Reaction will basically take place at C double bond O group called carbonyl group. So when aldehyde or ketone is reacted with PCl5, we get a geminal dihalide and POCl3, phosphoroxychloride, I told you earlier also. In place of PCl5, we can also use SO2Cl2. SO2. Wait a minute. Yes, in place of PCl5, sorry, in place of PCl5, we can also use SOCl2, that is thionyl chloride, we used earlier also. And this will also lead to the formation of geminal dihalide plus byproduct will be SOCl2, right? So these were total 3 plus 3 plus 4, total 10 methods of preparation of alkyl halides from alcohols, from aliphatic hydrocarbons, and by some special methods.